Physical AI begins with a hard truth. The real world is partially hidden, noisy, and constantly changing. A single camera can be blinded by glare. A LiDAR can miss texture. GPS can drift. Microphones hear echoes. Reliable robots do not ask one sensor for the truth. They combine complementary measurements into a shared, continuously updated estimate of reality. Cameras deliver dense visual context at low cost. They recognize signs, faces, tools, hands, and subtle surface cues. Modern detection and segmentation networks turn pixels into useful categories and boundaries. But cameras estimate depth imperfectly, suffer in darkness, and can be confused by reflections or unusual lighting. Their strength is semantic richness, not guaranteed geometry. Stereo and depth cameras estimate distance across an image. LiDAR actively measures ranges to form precise point clouds, often at long distance. These sensors make curbs, shelves, obstacles, and room structure visible in 3 dimensions. Yet they can be sparse, expensive, affected by weather, or uncertain on reflective and transparent surfaces. Geometry needs companions. Radar measures range and relative velocity using radio waves, making it valuable through fog, rain, dust, and darkness. It is especially useful for vehicles tracking fast-moving objects. Its resolution is usually lower than camera or LiDAR, so a radar return may tell you that something is approaching without precisely identifying whether it is a bicycle, truck, or guardrail. An IMU reports acceleration and rotation. Force and torque sensors reveal contact, grip, and load. GPS offers global location when signals are available. Microphones add speech, alarms, and environmental cues. Together, they let a robot estimate not only what is around it, but how its own body is moving and interacting. Proprioception is as important as vision for stable physical behavior. Imagine an autonomous car approaching a foggy intersection. Camera features suggest a person near the curb. Radar detects a moving return. LiDAR outlines an object, while GPS and IMU stabilize the vehicle pose. Fusion aligns these signals in time and coordinates, weighs their reliability, and produces a cautious track with uncertainty. The result is a safer braking decision than any sensor could provide alone. Kalman filters combine noisy measurements with a motion prediction. Extended Kalman filters handle nonlinear motion, while particle filters represent several possible hypotheses when uncertainty is complex. These methods are not glamorous, but they are foundational. They continuously ask what the system expected to see, compare that with what it measured, and update its belief without overreacting to noise. SLAM, simultaneous localization and mapping, lets a robot build a map while locating itself within it. Visual odometry estimates motion from image sequences. Modern systems often blend these with inertial and LiDAR data. The key insight is circular. A map helps localize the robot, and a reliable pose helps build the map. Fusion breaks that circularity with repeated evidence. Object detection answers what and where. Segmentation draws precise regions. Occupancy estimation asks which volumes are free, occupied, or unknown. 3-dimensional reconstruction turns multiple views into usable geometry. These algorithms transform sensor streams into a scene that planners can query. The goal is not a pretty visualization. It is an actionable model with locations, shapes, motion, and confidence. A perception stack should output more than labels. Robots need tracked objects with velocity, free space they can safely enter, boundaries they should avoid, their own pose, and explicit uncertainty. Unknown space is a first-class output, not a failure. A machine that admits what it cannot see can slow down, scan again, or choose a safer route instead of pretending. Fusion can fail when sensors are miscalibrated, timestamps drift, coordinate frames disagree, or one sensor becomes silently degraded. A camera image and LiDAR cloud that are offset by a fraction of a second can create a dangerous phantom. Production systems monitor sensor health, validate cross-sensor agreement, and degrade gracefully. More inputs are helpful only when their reliability is understood. Sensor fusion begins with calibration. Each camera, LiDAR, radar, IMU, and robot joint has its own coordinate frame. Extrinsic calibration establishes where the sensors sit relative to one another. Intrinsic calibration corrects lens and measurement properties. Without a stable shared frame, accurate individual sensors can still create an incoherent and unsafe scene. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Perception is the robot's evidence engine. Cameras add meaning, depth, and LiDAR add geometry, radar adds resilient motion cues, and body sensors reveal movement and contact. Fusion turns those partial views into objects, maps, free space, and uncertainty. That shared estimate is what planning and control will trust, challenge, and update on every cycle. Robots move while sensing. A LiDAR scan can span time, a camera exposes over an interval, and an IMU updates rapidly. Fusion compensates for this motion and aligns timestamps so all evidence describes a coherent instant. This is particularly critical for fast vehicles, drones, and arms, where milliseconds can shift an object by a meaningful distance. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. Multi-object tracking associates noisy detections over time to estimate identity, position, velocity, and likely intent. A person briefly hidden behind a shelf should not vanish from the robot's belief. Tracking prevents jittery behavior and gives planning a stable forecast. It also exposes ambiguity when two similar objects could plausibly be the same target. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. A perception system should be tested across darkness, rain, glare, dust, clutter, unusual objects, sensor faults, and edge cases that matter to the deployment. Average accuracy alone can conceal dangerous blind spots. Evaluation must include calibration quality, latency, uncertainty, and downstream safety impact, because the purpose of perception is dependable action rather than impressive labels. This matters because physical environments punish assumptions that go untested. Engineers validate this capability across varied conditions, measure confidence as well as average success, and retain clear fallback behavior. The lesson is practical. A robot earns autonomy by making its assumptions visible, checking them against fresh evidence, and choosing a safer response whenever the evidence is weak. In the next layer of the course, remember this discipline. Every estimate has a source, a timestamp, a coordinate frame, and a confidence level. When those are explicit, a robot can fuse evidence responsibly. When they are hidden, even sophisticated models can make confident mistakes that downstream planning cannot safely repair. This discipline is what makes a machine cautious, legible, and reliable when conditions change.